Hello everyone. In this video, we are going to look at some of the range and velocity sensors that are common in robotics. And I know you probably have heard, read, or used, read about them or heard about them or used them, but I just briefly want to mention a little bit about them. And they are 2D structured light range sensors, LiDARs, both based on time of flight and phase shift, and Doppler effect for measuring velocities. So the first one and the last one are for distance. The middle one is for velocity directly. Although when you have range, you can numerically take time derivative of that and get an estimate of velocity. But Doppler effect sensors are the ones that directly give you velocity. You don't need to perform anything on them. The material here are coming from our textbook, Autonomous Mobile Robots, Introduction to Autonomous Mobile Robots by Sigurd Nurbakhsh and Scaramuza. And these two this one, the second one is a website. The third one is like a file, a PDF file, which is really great. So let's get to it. The first one is structured light range sensors. This is the kind of thing that you have in a 3D scanner as well. So if you want to know how a 3D scanner works, many of them are working based on a structured light. Not all of them, but many of them do. Because some of them are also based on the time of flight as well, like a LiDAR. So what does it do? It projects a pattern of light onto a surface, and then this light pattern will be deformed because of the surface topology. So depending on how high that surface is at that point or low, is it basically like a mountain, or is it like a valley or something? Those will deform this light pattern on the surface differently, and then a camera here on the side is looking at that. Okay, and based on those deformations, it can interpret the surface elevation, or in this case, basically it's like a range or a distance as well. So here you see that I have a light projector that casts light at a specific angle alpha, okay? And then this is like a surface, a simple surface you have, which is kind of like a truncated cone. If you shine light on it, like a single line, which is used for 1D scanners, then what you will see is basically something like a profile of it, like a cross section of it, of course, with angle. But you will see that this light in the middle have this shift D, or you might even call it disparity. And then the actual physical height in the part can be related to D and alpha. If you look at geometry here, you can clearly see that the relation between H, which is in front of angle alpha, and D, which is adjacent to it, is H equals D tangent of alpha. So if you want to look at a 1D, basically structured light, that's kind of the simplest thing, is to cast one single parallel line on it and look at the cross section. And based on these different D's at different points, you get different H, and you can interpret that. Okay, so you can get the height of the object, but you can do better than that. So this is just like a simple scanner. But I'll show you that you can basically actually measure the depth Z as well as the X, or the image projection, or in this case, not image projection, X is the actual location of the object. So you can do 2D scan X and Z based on U, which is the position pixel in the image, and the triangulation angle alpha. So let's talk about those. But again, what kind of structured light, what kind of pattern would you shine on the object depends on whether you want to do a 1D scan, 2D scan, or so on. So if it's a 1D scan, you go with a single line. If you want to measure the light in several directions, but not continuously, only at the specific spots, then you can basically shine this kind of pattern, right? A bunch of simple dots, bright spots. If you want to do continuous measurement along several lines, then you can go with several parallel lines, something like a barcode. But if you cast a grid on it, a 2D grid, now you can do perfectly 2D scan, and you can locate X, Y, and basically the 2D deformation. So here, this alpha, the angle at which the light is shining on the object, is called the triangulation light, and D is clearly the shift in the stripe position or the pattern position in the image due to the actual height h. Now, if you look at the 2D version of it, as I said, and the distance between the center of the laser pointer and the lens of the camera, you call it baseline B. U here is this position of the pixel measured from the center. F is the focal length of the camera. Alpha is the triangulation length. Using simple trigonometry, you can show that the X position, which is here basically the horizontal position of the pixel with respect to a camera frame in this case, right? It is basically going to be B times U over F cotangent of alpha plus U, and Z, the depth, is B times F over F cotangent alpha plus U, okay? So you can measure both Z and X, right? And of course, if you look at the image from another angle, you can measure Z and Y instead of Z and X, so you can really get all three coordinates of any point on the surface. And what we most of the time want is this Z, the depth, but most of the other times, depending on what we are doing, like if we are creating a point cloud of the environment and so on, we not only want depth, we might need to look at other patterns on the surface of the object too. So we might need X and Y as well. Most of the time, you at least need one of them in addition to Z. So these are some simple tricks, and again, it all comes from these similar triangles here and these coordinates, right? So for instance, F cotangent of alpha, this is F. This angle here is like your alpha, correct? So that distance from here to here, that is F cotangent of alpha. And then you add it to the U, which is the distance of that pixel to the center, and you add them together. That's the total deviation or shift of the pixel to the right or to the left. Okay, so you see that one there, and then you can compare it to B times U as well. And here you can see B. So here you have several, as I said, similar triangles, right? So you have this triangle that you can compare with this one, or you can look at this kind of half triangle with the half triangle, and easily by a simple similarity between the triangles, you should be able to calculate that. Also, for this kind of structure light systems, we define two gains or two sensitivity terms. One of them is the sensitivity of what we call the image position or image resolution in this case with respect to the depth changes or the ratio of image resolution to depth resolution. This is what in this system we call the triangulation gain or GP. And GP, if you take a derivative of U with respect to Z, look here, Z and U are related. If you find U as a function of Z and take a Z derivative, you are going to get this one here. And similarly, you see that alpha and U are related as well from this formula. So if you find alpha and take a Z derivative, this is the sensitivity of the angle with respect to the depth, G alpha, and that is going to be this one here. Now, what's interesting in both of them is both of these sensitivities, if you look at them, they both are inversely proportional to Z squared. So the further down the object, these sensitivities are going to be smaller. Okay, so when the object is close, a small change in the depth will cause big changes in the angle or big changes in the image pixel location. But when you bring them all the way down here, far away, then a little bit change, of course, is not going to cause much of a change in alpha or much of a change in the U. Okay, so this is the relation. Also, you see that the triangulation gain is proportional to the focal length and to the baseline, and the same for alpha. So if you want to get a more sensitive system and better, more accurate system, you need to use a bigger baseline. Okay, a bigger baseline distance between the laser and the camera will give you better gains, as well as, of course, a bigger focal length, a bigger lens. So this is very simple introduction to 2D structure light and the relevant formula. So this is, as you can see, it is used to measure depth or range, but it can also give you other XY coordinate as well. Now, let me skip to the third one because this one is also used for range. Let's talk about this first, and then we go to the Doppler because Doppler is about velocity. So the third one is the one that you have seen a lot and you probably have used a lot, a LiDAR, which is a light detection and ranging sensor. The way it works is it typically sends a light pulse like a laser, and the laser will hit the object and comes back. And then with two different mechanisms, they can measure the distance to the object. The first one, which is the simplest thing you can imagine, is called time of flight. So TOF LiDARs are the LiDARs that they send. So this is an object, and they send the light to it. So it goes, hits, and then comes back. If this distance is d, the total distance that the light travel is 2d. And this total distance equals the speed of the light, which is c times the time it takes to go and come back, t. So from here, if you solve for t, it's going to be ct over 2. Okay? Now, the thing is about these is the c. This c is a very large number, right? Remember, this is 3×10⁸ meters per second. Okay? That's a big number, 300 million meters per second. That's not a small number. So if you're looking at, for instance, an object that is like 100 meters away, right? Then the time that you expect it to go and come back based on this formula is going to be 200 divided by 300 million. Okay, so let's see if my math lab is there. So 200 divided by 300 million, correct? So that's 3, this is 6, this is 8. There we go. And you see it's 6.6 e to the negative 7. 6.6 e to the negative 7. So let's write it. Or we can write it as 6.67, right? If you round it, 6.67 nanosecond. Now, of course, this is not bad, but again, you have to measure times that are less than 1 microsecond, okay? And this is for a large distance. Now, imagine the object is only 1 meter away. Now what? Now you're looking at 6 nanoseconds. Imagine the object is below 1 meter. Now you're going into picoseconds. So if you want to go into centimeter accuracy with these devices, you need to measure times of order picoseconds. Okay? And measuring times of order picosecond needs special circuitry that can measure that kind of fast time. Okay, and they are not necessarily cheap. So we'll talk a little bit more about it, but although these guys have a good total detection range, but their accuracy is limited to the circuit they have. So if you look at their accuracy, they are moderate accuracy, and we'll talk a little bit more about it, although they can measure up to a few hundred meters. Their speed is, of course, very fast. But since they need very fast timers, they are complex and they are quite a bit costly, okay? But we can use them in robotics, in drones, and in automotives, especially for automotives and drones. For outdoor applications, these could be relatively good because the distance to the objects are quite a bit larger than a few centimeters and so on. So this is a simple LiDAR. And that's, by the way, the same thing that an acoustic system does. That's the same thing, except that c is now going to be the speed of the sound wave. The problem with acoustic is we have to replace this with v, and the speed of the sound, you know, that's square root gamma RT in the air. So that speed of the sound in the air, that does depend on the temperature. So if you are basically using an acoustic sensor outside where the temperature is not under control, depending on the temperature, the speed of the sound might not be exactly like what you always think, 342 meters per second or something. It could be smaller or bigger, where the T is, of course, in kelvins. So the thing about the acoustic systems is, first of all, their range is much more limited than lasers. Second of all, they depend on the temperature, but good thing about them is if it's rainy or something or fog, acoustic systems can do a little bit better than the laser does, because laser can really not bounce back properly, especially if there are visual issues like, as I said, fog or rain. So each one have their own applications, but typically we use acoustic sensors for a shorter range for indoor applications, and we use laser for mostly outdoor applications, although again we can use them for indoor as well, just we need to know the limitations. Now there is another type of mechanism for LiDARs for measuring the distance, and that is based on the phase shift. So instead of measuring the direct time of arrival, t, that takes it to go and bounce back, they measure the phase difference between outgoing beam and incoming beam or reflected beam. Okay? In this case, the wave that you send is not just a simple light with no amplitude modulation. In this case, you modulate or change the amplitude of the signal and send, for instance, a sine wave, so you can easily measure its phase. So when the signal goes and it comes back, of course, it took it some time to travel, and this time can be translated into a phase shift. So if you put back the return signal versus the original signal, they will not have the same phase, because there is a time difference between them. And based on that time difference, or in the phase difference, we can assume how much it has traveled. So if the signal being sent out is a sine of 2 pi ft, where f is the frequency in hertz, the return signal or reflected signal is going to be a prime, not the same magnitude, because not all of that signal is reflected back, sine of the same frequency, but plus a phase shift. Now this phase shift is related to the distance to the object d, as well as the frequency of the signal and the speed of the light. Where does this come from? Well, you know that, again, it takes some time to go and come back, right? T. How much is this t? Based on the formula we just saw, t equals 2 times distance divided by c, correct? That's the time. Now the phase shift, delta phi, if you want to call it delta phi, is going to be the frequency times the time, so 2 pi ft. So it is going to be 2 pi times f, and then for t, we're going to plug it in, so 2d over c, and guess what? If you look at here, it's going to be 4 pi ft over c, which is exactly this one. Okay, so that is the formula for phase shift, and from here, if you solve for the distance, your distance is going to be this one in this box, c phi 4 over 4 pi f. So the distance depends on the speed of that light, which is mostly a constant number. Of course, it depends on the density of the environment, the frequency of the modulation, and the phase shift that we have to have a mechanism to measure. How do we measure phase shift between signals? If you're interested, one video I recently published under playlist vibrations, and that was about measuring phase shift between two signals, okay? So I use a Hilbert transform and I use a cross correlation. I showed you these are two simple methods for measuring phase difference between signals. Please watch that video and you're gonna learn from that. But if we can measure the phase shift between them and plug it in here, then we can measure the distance as well. Now, you might say, why would you use this? Why don't you use that top one, right? Because they are equivalent. You see, the second one formula is derived from the first one. Well, let's talk about it. Why some people will choose these phase shift systems as opposed to the time of flight. So, the reason is these guys are more accurate than time of flight. Why? Let's find out. I just showed you that if you want to get into centimeter accuracy for the time of flight, you need timers that can measure picoseconds. And these timers are not cheap. Okay, so most of them do not go that far. And because they cannot measure that kind of time difference, they are not going to be super accurate for short distances. Now, let's see what happens to a short distance measurement if you use a phase shift. So, for instance, let's say that the modulated frequency that I use, f, is going to be 10 megahertz. So, f is going to be 10 megahertz or 10 to the 7. The wavelength of the modulated signal is going to be c over f, where c is 3 times 10 to the 8, divided by that is 30 meters. So the wavelength of this signal that I'm sending out is 30 meters. Good? Now, if I want to have a phase precision of only 1 degree, if my system that measures the phase difference, phi, can only do it up to 1 degree, no less. So it cannot do sub-degree, but it can measure, it has an accuracy of up to 1 degree. Okay? Then what is the accuracy I can measure to? Well, it's going to be that 30 meters times 1 degree divided by the whole 360 degree, the range that the phi can be, over the accuracy times the wavelength, and it is going to be 8.3 millimeter. Do you see that? It is 8.3 millimeter. I'm already below a centimeter. Okay, I'm already below a centimeter with not a super fancy phase measurement accuracy and not with a basically super low frequency. I'm doing, or super high, a reasonable range. I'm doing great here. Okay, so I can easily get better precisions than TOF systems. Okay, so that is the advantage of the systems. So in terms of accuracy, their accuracy is high, but TOFs are moderate. Now, their speed is high too, because measuring phase is not hard. Since they need, of course, phase detection electronics, but they are cheaper than those extreme fast timers, so their cost is lower. And we can use them mostly for indoor automation, for augmented and virtual reality and phones. And you might say, why would you use them for indoor automation as opposed to outdoor? Because they have a short range. While the TOFs can measure up to several hundred meters, these guys typically won't be used for more than 10 meters. Why is that? Although they are accurate, why the ranges are not too good? Well, let's take a look here. So the reason is this phi, which is the phase, is a periodic function and it repeats itself every 2 pi. So the maximum distance that you can measure without ambiguity is going to be, based on this formula I just showed you, is going to be c times maximum phi, which is 2 pi, divided by 4 pi f. So if you simplify, you are going to get these 2 pi and 4 pi cancels. You get 1/2 of c over f, which is lambda over 2. So if you were wondering why here the distance is related to lambda, you can see it here. D is related to lambda. Okay? And or you can write this also in terms of lambda, because c over f is lambda, so you could write also this as phi, correct? Lambda over 4 pi. So you see d is proportional to lambda times phi. Okay, and that's exactly, by the way, what is being used here. So if you're wondering where is this part coming from, that a phi divided by multiplied by lambda, that comes from this formula here. Okay, so going back to our discussion, well, you see the maximum that you can measure is lambda over 2. So remember here we said the lambda is 30 meters for that frequency, right? Then over 2 is about 15 meters or so, sometimes even less because we don't go up to 10 megahertz. And then you might say to yourself, well, if I make this lambda very large, then I can measure bigger distances. For instance, if I make this lambda 400 meters, then I can measure up to 200 meters. So now I'm comparable to a TOF. Yes, but what happens if you want to measure with such big lambda? In order to make lambda very big, since c is constant, right? Look here, c is constant, and lambda is c over f. Since this guy is mostly constant, to make this guy bigger, you have to bring your frequency down. So instead of a 10 megahertz, now you have to go, for instance, for a 1 megahertz or half a megahertz or something, okay? Well, although that gives you a much bigger range for measurement, what's the problem? The problem is, of course, in this formula itself. If you look here, when I make this f small, then d, the sensitivity here, will jump bigger for a small change in f. Because if I do partial of d here with respect to f, you can see that it is going to be negative c phi over 4 pi divided by f squared. So you see a smaller f, like 2 times a smaller, make this sensitivity 4 times bigger in a negative manner, and so you're going to lose your resolution. So your resolution of the device will be smaller. Although you can measure bigger ranges, you lose your resolution. And since the major promise of this system is good resolution and high accuracy, you don't want to sacrifice that for a bigger range. So you use them for indoor automation where the range is small itself, so you can get a better resolution. Okay, so this is a difference between them. The last thing I want to mention before we end this video is, in the time of flight, you send the signal, it comes back, you measure the time lapse, okay? But in the phase shift systems, we are using a continuous wave signal, like a sine wave. And so, because we are sending this sine wave and then it comes back with a phase difference, and the system is not going that fast as like last time, we have more chance for integration time and narrowband filtering, because the signal that is sent out and comes back in, they are not going to be identical. If you look here, not only their magnitudes are not the same, their phases are not the same. If there is any interference from the environment, this wave of this reflected signal could be quite a bit different with some noise. So you might need to do some filtering on this reflected signal before you do an accurate measurement on the phase shift. And because this system is, as I said, working with continuous wave signals, you can do a better chance, you have a better chance of doing a filtering, because you are not measuring time and you don't need to be fast in terms of picosecond. So you can do a better filtering, and that means your system is less sensitive to noise. And that is another reason that your accuracy is higher in phase shift systems than TOF. Okay? So hopefully you see why these systems are more accurate, but at a lower range or a smaller range. So in this video, we looked at so far the 2 major systems about the structure light and the LiDAR systems. And I just forgot that I actually have to talk about Doppler effect. So I'm not going to finish the video right yet. Let me talk briefly about these Doppler effect sensors before we finish the video. I need to talk about those as well. So the Doppler effects are not for measuring range, they are for measuring velocity. They directly give you velocity, or speed actually, to be accurate. So how does it work? Well, probably a lot of times you have heard that when an ambulance is coming toward you with the siren going on, with the wave that it is sending, if the ambulance is getting closer to you, you hear a higher pitch frequency, or higher pitch signal, or higher frequency signal. But if it's getting away from you, you are hearing a lower pitch or lower frequency signal. Okay? Why is that? Because if this ambulance is fixed and it is not moving, okay? Now, that's not an animal, okay? That's an ambulance. If it's creating waves and not moving, these spheres, or in 2D, these circles, are gonna be all concentric and spreading out. So their center is still gonna be at the siren location and they will spread out. But when the source of the signal, which is the siren, starts moving, what happens? In the area in front of it, these waves are going to be closer to each other, and in the area on the back, they're going to be further apart, right? Because you have this velocity v. In addition, this is the v of the object, in addition to the v of the sound. So here, those velocities are added, here they are subtracted, okay? Therefore, in this direction, you can see basically a bigger frequency, because if you remember, we had the formula lambda was c over f, right? Or if you want f is going to be c over lambda, correct? So this c, this is for a basically light wave, but it could be acoustic wave, so I can replace that with v if you want, because it's not, in this case, LiDAR, although it could be. We'll talk about it. In this case of siren, it's acoustic wave. And you clearly can see that when the V, the relative V here, goes bigger, because it's sum of these two, the frequency goes bigger. And when they are subtracted, so in this area, V relative is smaller, then the frequency is going to go smaller. So this is like a V relative. So you see that, okay? That's the Doppler effect. And so that is basically a way for us to measure this V of the object. If we know V of the sound, which we do, then based on the change in the frequency of the signal, so if I can look at this frequency of the original signal, and the frequency of the received signal, either in the front or on the back, if I can measure this V relative, because again, I know lambda and I know f, I can measure V relative, and if I know V of the sound, I can measure V of the object from that, okay? Or I can do it based on the frequency shift. So based on this frequency shift, which is from the front and the stationary one, or in the back and the stationary one, I can measure the velocity of the object. So what is the formula? The formula is very simple and you can easily show it. So here we assume that the source is stationary and the object is moving directly toward or away from that. In this case, you can show that the shift in the frequency. What is this shift? This shift is the difference between the frequency of the actual sound wave and that is being emitted, and the one that is perceived by the receiver, okay, or the object, right? So it's the frequency of the source and the frequency received by the object. That's the difference, is called delta F. And then 2v cosine theta over c. Now this c is the speed of the wave. if your system, the Doppler effect sensor, is using electromagnetic wave like radar or laser, c is going to be the speed of sound, the speed of light. But if they are using acoustic waves like this, ultrasonic wave most of the time, then that c is going to be the speed of the sound. So the c, if you don't like it, you can replace it by v if you want, but that v and this v are kind of the same. That's why here we are using a c for that notation. So c is the speed of the wave, okay? And then delta f is the difference between those frequencies. V is the one that you are interested, that's v of the object. ft is what? That's the transmitter frequency. So that is your transmitter or the source frequency. And cosine theta is for the cases that the object is not directly coming at you, it is an angle. So if you look at it from the top, the ambulance might not directly come at you and it comes at some angle. So you're looking here, right? And the ambulance, instead of coming along this line, the ambulance, if you look at it from the top, is traveling like that with velocity v. In this case, you have this angle here, this angle theta. Okay? For the case of, it's like a head-to-head collision or something, head-on collision, that theta is 0, but it's not always 0. So you can calculate the shift like this, and then if you want, you can divide that ft by c, and that is going to be 1 over lambda, so you can also write it like that. And if you are interested in the velocity, you solve for velocity, and this is the velocity of the object. Again, assuming that the source is stationary, the object is moving directly away or toward that. Sometimes it's backward. Your object is stationary. Your source is moving toward that. Again, that is like a relative velocity. Formula applies to both scenarios. Now, briefly, if we want to talk about the types of Doppler effect sensors, so they are radar-based, they are LiDAR-based, they are ultrasonic-based, so we can use all of them, and there is a special kind that is for vision, is called optical flow-based. What is optical flow? That's the apparent motion of the pixels in an image. If you want to know about optical flow, I have several videos under my playlist, Computer Vision and Image Processing. You can learn about optical flow. So the radar-based, they are using radio or microwave signals in gigahertz range. The LiDAR ones, they are of course using basically light, lasers. The sound waves, they are using high frequency sound, ultrasonic in kilohertz range, and these guys are just using the images and look at the pixels. For radar Doppler effect, we typically use them in traffic sound guns. These are the ones that police is using. They are using radar-based Doppler effect sensors, and they can be used in drones. For robotics, as I said, we mostly use the LiDAR-based, and for autonomous vehicles. For medical imaging, we can use ultrasonic ones, and also for indoor robots. So with these ultrasonic ones, you can look at the flow of the blood in the veins and you can measure their velocities. Okay, so these are really great. You can look at the velocity of the blood in your veins. And the optical flow ones, again, you can use them for indoor navigation and drones as well. So these are different types of Doppler effect. And finally, their advantages and disadvantages. Their advantages, they can measure the velocity with no contact. They are very fast. They are very accurate, especially at high speeds. And even for low light condition, the radar systems or the ultrasonic ones also work. Okay, so they are fast and accurate. Their disadvantage is angular dependency. They are accurate when the object is moving along the line of sight. Remember here we talked about this angle theta. If the object is moving in this direction and you are fixed at this location, what happens? Well, one time the object is here, one time it is here, one time it is here. And so if you look at the line of sight that you have and the direction of motion, the angle is going to be this. Here, the angle is going to be this. And you clearly see that the angle is changing. So you have to have a way to measure that angle. If not, then the number that you get is clearly not going to be accurate. Of course, they depend on the source of the wave or the object to move. So if they are both stationary with respect to each other, then they cannot be used. Okay? That's one thing. And of course, the goal of these is not to detect objects. The goal of them is to calculate the speed of moving objects. But again, you cannot use them for object detection. So if your goal is to filter out the objects that are moving, right, like you do with computer vision and so on, well, they don't give you anything as long as the object has not moved. But with the camera, you can still use methods like YOLO or so on and detect objects. Now, multiple path reflections can cause errors, okay? So if the wave does not go directly and come back, that's for the case of LiDARs, but for these ones, if something is on the way and you don't directly get those changes or shifts in frequency, you might get some errors. Now, that's not super common, okay, unless, again, like when you're police measuring the speed of somebody, some person jumps in between your camera and the car that you are measuring. And depending on the type of wave, range is going to be limited. Typically, ultrasounds have a lot less range than radars. And finally, the last thing is they can suffer, the ones that are working with laser, as I said, they can suffer from fog and rain. So environmental condition can affect their accuracy. So hopefully this brief video on these mechanisms for measuring range and velocity in robotic systems was useful to you, and I'll see you in the next lecture. Thank you.